Hello everyone, Doug Simonian over at New York Metro Weather with your latest video discussion. We have a lot to talk about as we discuss the upcoming powerful winter storm coming up for the southeast parts of the coastal mid-Atlantic and the coastal northeast and New England as well. But it's not going to act like a typical nor'easter, typical snowstorm because the storm is going to be strengthening so rapidly off the coast and take on such a relatively low surface pressure, relatively speaking to the typical coastal storm, that the precipitation fields are going to act somewhat irregularly compared to usual cyclones, and that presents a lot of forecast challenges going forward. So let's just start by taking a look at the GFS model at 500 millibars, so the middle of the atmosphere. The shading is the vorticity, and the sticks, for lack of a better term, are the wind barbs, are the wind directions. So we can see that on the GFS model, valid for right around now, the time I'm recording the video, there's two main features of energy, so to speak, in the atmosphere. There's one strong shortwave trough in the southern plains about to enter the Gulf of Mexico, and this will continue to amplify over the next several hours as it actually taps into Gulf of Mexico moisture and generates a lot of convection and latent heat release for heavy precipitation in parts of the southeast, and that also presents a lot of complications moving forward. And then this piece of energy in the northern stream is also going to dive southward downstream of this large ridge and try to act as a quote-unquote seesaw effect, whereas what goes down on the west side has to come up on the east side in order to amplify the trough downstream to send the main southern shortwave up the coast. But it depends on exactly how these two pieces of energy interact, as well as a third piece of energy somewhat emanating from the tropospheric polar vortex, and how that interacts once these two pieces of energy are already interacting off the Carolina coast. That's also going to determine the orientation of the precipitation shield. So let's just get started by looking at the progression. So we see the southern shortwave consolidates and amplifies in the lower Mississippi Valley, right in between New Orleans and the Florida Panhandle. Usually a pretty good spot for amplification if you want a snowstorm along the East Coast. However, the heights along the Northeast are still somewhat compressed by the initially somewhat elongated tropospheric polar vortex, so that often could be a somewhat of a suppressing feature. But again, the southern stream shortwave, with how strong it is and how much it taps into the Gulf of Mexico, will release a lot of latent heat into the atmosphere. And latent heat in itself is something that can trigger height rises downstream, because heights are pretty much a byproduct of warmth in the atmosphere. If you have higher atmospheric heights, that means there's more warmth throughout the column. So if you're releasing latent heat into the atmosphere, you're inherently going to raise the heights downstream. So it is a realistic process that actually occurs in a lot of our storms that forces the models to trend westward with storms in the last minute, and we will see how the GFS has really gone towards doing that. Even if you look at the trends, this was the 12Z run, the 6Z run, the 0Z run, and then yesterday. Look how weak it was with the southern stream shortwave just 24 hours ago. Really not that impressive. A little kind of sheared out. But then as we move forward in time to the present, it's becoming much more of its own shortwave ripple and consolidating right in the Gulf of Mexico, and that helps for more convection to fire off, and thus latent heat release and height rises along the Atlantic seaboard, which is one reason why the GFS has rapidly moved west in its last few model cycles. As you scroll through time now, this is Wednesday afternoon, we see the streams of energy somewhat interacting but not completely off the southeast coast. It's a very tough fine line, because if this northern stream energy were to dive southeast and try to quote-unquote phase with the system, it wouldn't necessarily be a clean phase right away. So this would actually somewhat act as a suppressing to the storm to dampen the heights and compress it. If you want a snowstorm, you actually kind of want the southern stream to remain strong and separate so that it has the most quote-unquote room possible to breathe and vent and release additional latent heat downstream without having any of that latent heat compressed by the northern stream. So as this northern stream trough dives southwest, well, more so southwesterly, relatively speaking, instead of southeasterly and interacting with the storm directly, that gives the storm more room to amplify as well. And if you look at the trends, even the 12Z run, the energy was getting suppressed more to the south because there was more of a direct interaction. At 18Z, the southern stream is a little bit more separate from the main trough. See, the trough at 12Z kind of connected a little bit more with the southern stream, and then at 18Z, you see the heights are just a little bit more separated. Like the southern stream is more of its own singular entity rather than the 540, 546, 542 height contours all directly interacting linearly with the gradient. We see here the gradient is much tighter offshore with the southern stream. And then there's a wider gap, a separation between the northern stream and southern stream, which gives us, the southern stream energy more room to release convection. So that is a big part in the northerly trends that we've seen on the GFS model. And the fact that these trends are occurring so rapidly definitely gives credence to the idea of the storm moving northwestward. Look at some of the previous runs. The southern stream was barely even noticeable except for a couple of ripples of vorticity. There was just one long wave trough. But then again, as we scroll through time later in the runs, look how much more separate it got. So that is huge if you want a snowstorm along the East Coast, because without that separation, the northern stream is going to act as an inhibitor of precipitation along the East Coast. But instead, now that they are separated, the northern stream can actually continue to provide the additional quote-unquote seesawing effect to constructively feed back with the height rises the southern stream is providing. So it'll be interesting to see how that plays out. And as we scroll through time again, we see that the southern stream still has room to vent. The northern stream is diving south, but not directly colliding, but diving southward enough to help with the height rises along the East Coast. And you're actually able to get some positive vorticity advection right near the coastline to help snow form along the East Coast. We look at the previous 12Z when the southern stream was that was shunted further southeast because the northern stream was more compressing. And then even on the 6Z run, look how far southeast the southern stream was, because again, the northern stream was more compressing. But now the northern stream is backing up westward. The southern stream has more room to breathe, and you're getting heavier precipitation. So these trends occurring so rapidly amongst all the global models, not just at GFS, all the global models are trending more towards having that evolution with the southern stream more separate, is definitely a red flag for the storm trending westward with time. Now that doesn't always mean more heavier precipitation. It generally does, but in this circumstance it may not always do that, and we'll talk about why later. Though if you're along the coast, like New York City and eastward, there probably will be more of a one-to-one correlation between westward storm movement and snowfall, but west of New York City, there's not necessarily a one-to-one correlation between westward movement and snowfall. You can also see the trends at the 250 millibar jet. The most startling trend is occurs pretty much right away, but I'll just go to the hour 42 panel on the 18Z GFS. We see, we have a classic dual jet region, a very strong southern stream jet, and the low pressure is in the left exit region of that jet, and it's in the right entrance region of this very strong confluence jet near Newfoundland and northern New England. So a classic for venting, and with all the latent heat it already released for convection, and the fact that the storm started in warm waters and then kind of remained in the Gulf Stream before trying to cut back northwest is really just a classic recipe for rapid deepening of the storm. So that's why we're seeing such low pressures. It was 968 due east of Hatteras. It's very impressive and will break low pressure records for that latitude. But if you just look at the trend in the jet, we see, look how in the old model runs, how the jet was more compressed, due south to north, and you weren't really getting the jet further north to buckle westward. But as we move forward in time, look how the jet in northern New England is able to gradually buckle more and more westward and northwestward, right? Look at this. That buckling westward and northwestward is able to increase lift in the atmosphere further west as well. The right entrance region, the I guess the quote-unquote right quadrant before the jet streak begins, that area is where you get more enhanced lift or precipitation. See that the trends have allowed that area to move northwest, and it's a pretty rapid trend amongst the forecast models. Again, look how much the jet is moving northwest and buckling also. So that is able to allow precipitation that was originally consolidated near the center of the low pressure to expand westward along the coast. And that trend is also something that is undeniable amongst all global models. There are some, waffling back and forth among some of the mesoscale models regarding the exact surface low placement. Sometimes those quote-unquote trends are noise because there's no long-term real movement in those features. But this jet and that vorticity with the southern stream, those are undeniable trends that have occurred over a long period of time in the forecast models. So that is something that has to be weighed heavily going forward. If we look at the surface on the GFS model, we see that the storm, there's a dual low pressure center as the low tries to tuck in westward in response to the convection and latent heat release and the height rises. And then you actually get the predominant parent low taking over, tucked in right near Hatteras. That is much further west than any other model runs had it. Look how far offshore the low pressure was in the previous model runs. But then as you move through time, look how much it corrected westward every single run. So something certainly to a sight to behold as far as the trends are concerned. And then we see the low pressure rapidly deepen as it heads up the east coast. It still gets shunted a little bit out to sea because there is still, a little bit of resistance from the northern stream. So the storm can't make it all the way up the coast. Because you see the wind barbs that happen at millibars, they are pointed southeasterly and easterly, which does help bring in, saturate the mid-levels of the atmosphere and bring snow to the region. But you still get a compression of the height field in New England despite those trends. So the storm can't completely, make it all the way inland. So the H5 low kind of closes off southeast of southeast of Cape Cod, and then moves northeast from there. But still, it's much further west than the previous runs. But still, look at the previous runs of the GFS, how the storm was so far offshore, and now we're getting a rapid movement westward with more precipitation expanding into the northeast to the point where New York City is now forecast to get several inches of snow on the GFS, and all Long Island is forecast to get 6 inches plus on the GFS model. And of course, eastern New England could really get pounded as they will have some of the heavier banding associated with the rapid low pressure development. 960 millibars off our coasts, which is really impressive. We can take a look now at the NAM forecast model, and we can see that the trends have still generally been occurring the same way. Look at the southern stream as its own entity. The 12Z run was actually a snowier run than the 18Z run on the NAM guidance, because on the 12Z run it actually was a little bit more of its own entity, and the 18Z run, the 18Z run is a little more sheared out. So that there is still a little bit of a discrepancy in the trend in the mesoscale models compared to the global models. Although in the long term, the southern stream has still become more of its own entity. But either way, you get an impressive little shortwave energy, but that it gets compressed by the northern stream on the NAM model. But because of the NAM being a somewhat of a convective model, especially the 3-kilometer NAM, which actually allows for all convection, which means that there's no limit as far as how much convection impacts the storm's load track on the high-resolution NAM model. So we see that on this NAM model, the low pressure tries to tuck in towards the coast. And there's some extremely heavy precipitation falling in eastern Long Island and southeast Massachusetts that does back into western Suffolk and Nassau County and into most of New England as well. So from Nassau County and east on the NAM model, you are getting several inches of snow or even a foot plus in eastern Long Island and throughout a lot of New England. But because of the flow getting more compressed, the cutoff in precipitation is very sharp. And that's also something to watch out for moving forward. If we look at the NAM jet streak, we can notice why that happened on this particular run. This was the 18Z jet. It's a strong jet, but it got somewhat compressed. Look at the 12Z jet was a little bit more expansive. The 18Z jet got kind of compressed a bit. So that expansive jet allowed the 12Z run to be a big snowmaker for a lot of the East Coast with a wider precipitation shield. But then the 18Z run, the jet was further southeast, allowing for a drier solution, but was still, because of just how strong the storm is with all the latent heat release, you're getting heavy banding more just on the coast rather than further inland. Just some more of this beautiful IR simulation on a high-resolution Canadian model. This is a classic storm formation. The high brightness temperatures being denoted on this model, and you see it's a classic storm. It's going to form a pseudo eye-like feature along the coast, and if this were to verify, this is also a pretty good snowmaker along a lot of the East Coasts. And this is a model we do use, but again, it's just a model, it's a tool, it's not meant to be taken verbatim. Another thing that's going to be complicating as far as figuring out the banding is a deformation zone and subsidence. You often get a deformation zone where the banding expands and accumulates in a higher ratio well northwest of the surface low. A deformation is where it looks like the winds are going to converge, but instead they kind of spread out upon meeting. And you actually get a deformation zone in upstate New York and eastern Pennsylvania where looks like there's going to be some convergence with the westerly winds, but instead of just completely converging, they kind of spread out upon meeting there, right? And then further south, you actually get the same thing where it looks like these streamlines in eastern New Jersey are going to meet up with the streamlines in Virginia, but instead of completely converging, they also kind of spread out upon meeting. So in between that, where that spreading out occurs, you get some deformation in parts of upstate New York, eastern PA, and down into the western New Jersey and parts of the Delmarva. So you get deformation there for lift and precipitation. And then you also get diffluence closer to the storm center, where the winds are actually kind of spreading out a bit towards the low pressure center for some heavier precipitation rates across Long Island and further east. But in between those two zones, you actually get subsidence in a good part of New Jersey and northeast New Jersey. Even the humidity levels are actually a little bit lower in southeast New York and parts of Jersey. So you get some subsidence as well. But of course, the orientation of this could all change. If the storm continues to move further west, then the diffluence zone is actually going to shift further west, and you actually can get more banding for snow to expand further west as well. So it's really a tough forecast, but just goes to show that if you don't necessarily align the deformation zone with the core of the precipitation axis, you're not really going to get an expansive area of deformation banding. Ideally, you want the heavier precipitation to align with the right entrance region of the jet streak as well as the deformation zone. The right entrance region is still a little bit further east on the 18Z GFS, like the right side of where the jet streak starts. But again, if this low pressure were to move further west and the jet were to move further west, then you'd be able to co-locate the lift and precipitation with the jet region better to expand the precipitation as opposed to contracting it. Here are the trends on the European model. We see the same thing was occurring as on the GFS. The 12Z had the southern stream as much more of its own separate entity with heights curling up the coast, whereas on the 0Z run last night, there was more of a singular long wave trough with no distinct southern stream. So the fact that the European made this rapid of a shift goes to show that it's really not handling the storm very well at all and should not be weighed very heavily going forward. And the same thing occurred more so towards our latitudes as well, with on the 12Z run, the southern stream was much more of its own entity and tucked in towards the coast and separate from the northern stream. Whereas on the 0Z run last night, there was more northern stream interaction, so to speak, which kind of compressed the storm. However, on the European model, in the mid-Atlantic anyway, that interaction, that cleanliness to this trough and alignment to the trough actually led to some precipitation expanding a little bit to the west. And then on today's run, although the storm moved further west, you lost that alignment from the northern stream that expanded the precipitation further west. So you got heavier precipitation to the east, but then less precipitation to the west on the European model when the storm moved westward. So if the storm were to not move any further westward than what the European model has, then you're actually going to get an area of subsidence throughout the entire mid-Atlantic and into New Jersey, New York City, and western Long Island. However, if the European model were to keep moving westward, then the subsidence zone would move further westward, and you can still expand precipitation into the area as we go through time. But just a little bit more, just more so for fun, looking at the RPM model, just goes to show how a further west low will mean more intense precipitation, but not necessarily further west precipitation. This is the 21Z RPM model. It shows a very far west surface low pressure with extremely heavy precipitation across Long Island and southern New England, with light precipitation back further west. There's a subsidence zone with northwesterly winds. And then on the previous RPM model run, the storm was further east, right? This storm was much more tucked in on the 21Z run, and on the previous run, the storm was further east. But the precipitation was actually a little bit more expansive to the north, but also much lighter. So the further west low led to a lot more intense precipitation because you're combining intense pressure falls further west. You're more so co-locating it with the right entrance region of that jet streak, so you're able to align the forcing mechanisms for more lift in the atmosphere. However, when you're getting such intense lift around a very tight circulation, and when the low pressure is very strong and a tight circulation, a lot of times the mid-level forcing wraps around it more so. So you're not going to necessarily get the same aerial expansion. You might get a little bit of expansion with the jet, but overall you're actually going to get a little bit less expansion. So it's the best way to put it analogy-wise is you're going to need, for these trends to work out for heavy snow from New York City and westward, you're going to need 2 steps west with the surface low to get 1 step west with the heavy precipitation. That can be done with the latent heat release trends that we're seeing, but it's not a guarantee. You may end up getting a trend where the models show 1 more westward tick to this RPM solution, which would hammer Long Island and southern New England with heavy snow, but not necessarily lead to more heavy snow further west until you get that second push westward to where you kind of bust that threshold to where you are getting rid of the subsidence. So that's why there's really so many complications to this forecast, because there are even other scenarios where the parent low was further east, and then you got a second area of dual surface low pressure that expanded further west, that led to a second area of precipitation further west. That was shown on model run several days ago, but we have kind of trended away towards that and are now relying on the entire storm to move further west, which is tough to do, but is certainly possible with some of the model trends that we have been seeing. So it'll certainly be a lot of fun from a meteorological perspective to track the storm. But of course, with the storm this strong, 950 millibars off the coast, you get very intense surface winds, and combined with all the cold and the snow, there could be widespread power outages and high impacts. So this could be a dangerous storm as well. So please don't, especially if you're in New England, do not take this lightly. But But again, the keys moving forward towards the 0Z runs tonight and the 12Z runs tomorrow will be the interaction between the southern stream and the northern stream, and the location of the jet streak, and the correlation, if any, between a westward surface low movement and a heavier precipitation moving west correlation. But of course, with the trends in the global models, it does seem that there will be snowier trends tonight, but again, that cannot be guaranteed, especially for areas west of New York City. Alright, so we hope you enjoyed this video and that explained the complex intricacies of the storm. We will be sure to keep you updated over the next 24 hours as we track the storm as it gets closer to our area. So have a great night, and we'll talk to you guys soon.